guys, it's Jack. Today's lesson is on mixing acids and bases.
So today let's start talking about mixing acids and bases with a conversation about strong acids and strong bases. Here we'll mix 0.550 liters of 0.20 molar sodium hydroxide and 0.3 liters of 0.25 molar hydrochloric acid. What is the pH? This is really an excess reactants problem, as you can probably see, and you might remember these from our previous studies. So let's have a look and see. The balanced reaction looks like this one, where the sodium hydroxide and hydrochloric acid make sodium chloride and water. And I now want to use a mole table, not for equilibrium calculations. These are not concentrations, but just moles. So here we get the initial number of moles of sodium hydroxide. It's 0.110 mole. The initial number of moles of hydrochloric acid, it's 0.075 mole. We have no sodium chloride or water to start. So here are the values. Here we'll have the amount of each reactant that's consumed and the amount of the products that are produced here. These will be in moles. The limiting reactant, of course, is the hydrochloric acid, so it'll all be used up. Consequently, we'll be left over with 0.035 mole of sodium hydroxide, and this solution will be basic. We'll call this the change line here, initial, change, final. Okay, so there we have 0.035 moles of sodium hydroxide for a basic solution. The pH is then 14 minus the pOH. That'll be the negative log of this concentration. Remember, there are now 0.550 plus 0.30 liters altogether. If you make sure that all these data here are making sense, you can see where it all came from the volumes, and we'll just calculate this and get a pH of 12.62. It's basic as we expected. Now let's have a look at a case with a weak acid or a weak base. And depending on what's left over in excess, these can turn into equilibrium scenarios, and you'll see one of those happen here. So we'll mix 1 liter of 1 molar sulfuric acid and 1 liter of 1.75 molar sodium hydroxide and ask what will the pH be when this is all done. So there's 2 moles maximum of hydride ion available because H2SO4 is diproduct, and 1.75 moles maximum of hydroxide ion available. So here we have the balanced reaction with the, this is a stoichiometric reaction, by the way, for the sulfuric acid dissociating, and now we have the bisulfate ion dissociating in the second step. So here we have again a mole table, 1 mole of sulfuric acid, 1.75 of hydroxide, and after the reaction is complete, the sulfuric acid will be limiting, and we're left with none of that and 0.75 moles of the hydroxide ion. Transferring those values into the second reaction, we'll see that the hydroxide ion is limiting, and we'll be left with no hydroxide ion at the end and 0.25 mole of the bisulfate ion. Because there's bisulfate ion and sulfate ion still left in the solution, we have an equilibrium scenario, and now we'll use a proper ice table. So there's 0.25 moles and 2 liters of the bisulfate, no hydronium ion, and 0.75 moles and 2 liters of the sulfate ion. That's left over from the previous step. This reaction will shift to the right with a Ka, as we see. It has to go right because there's no hydronium ion. So to the right we go, and these are the final equilibrium concentrations down here. Pardon me. A little bit of calculator magic is going to help us once we get the Ka value written down here. So here's the expression, and we'll write that down. It's X times, again, 0.75 divided by 2 liters plus X, and so on the bottom. So we'll need to use some calculator for this, and I'll just quickly run these two values in. We'll graph Ka against Q, make sure you use an appropriate set of window constraints. Calculate the intersect here between these guys, and we get it at 0.00384 molar. So that'll be the hydronium ion concentration. So that'll be the hydronium ion concentration, and the pH of it is the negative log of that at 2.42, which is good. This winds up as an acidic solution as we expected. Notice, though, it wasn't a straightforward thing. We needed equilibrium because the bisulfate ion was in equilibrium and not a strong acid. So this solution is a buffer, and we'll just preview our next lesson a little bit here. Remember that a buffer, you've heard this before, is a solution with meaningful concentrations of a conjugate acid and its conjugate base. In our case, that was the bisulfate ion and the sulfate ion. Notice that these are the concentrations we had going in there. 0.00384 moles, it's not that really much in there of the acid. So what happens if you take some acid out here, then the equilibrium will shift to the right. If you add some in, it'll go left. And this solution here can absorb or release protons buffering. Anyway, that's enough calculating for today, and next time we'll see a powerful technique for these buffer solutions and for other pH calculations, and that technique is called the Henderson-Hasselbalch equation. So stay tuned next time for buffers, buffering, and the Henderson-Hasselbalch equation. See you soon, everybody. Do stay tuned for our next lesson lesson number 21, which is buffers and the Henderson-Hasselbalch equation.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!